Okay, any questions before we get started? Okay, so we finished up what we wanted to cover, I guess, in the fundamental theorem of Galois theory, say last time. Now we're going to talk about splitting fields and algebraic closures. So how many of y'all have ever heard of the notion of an algebraic closure? So I'm going to be, when we get to the algebraic closure, I'll be honest with you going in. I'm not going to be super hardcore. I'll just kind of give you, sort of talk you through a general kind of feel for it. To prove the existence of algebraic closures, not super hard, but it requires some technical set theory a little bit. And you need to know the distinction between set, class, and so forth. But we're going to warm up by talking about splitting fields. So let me just get started. Definition. Eight, 3, 1. Suppose you have a polynomial of positive degree. It's a polynomial over some field, capital F, of positive degree. So we don't want it to be constant. We say that F splits in F of X. Or sometimes I might say that the polynomial splits over F if F of X equals U X minus Rn with Ri and U and F with U not 0. Okay, so this is what I mean for a polynomial to split. It means it factors. So the U is, so think of the U as kind of the leading term of the polynomial, right? And of course, I want that to be non-zero because I don't want the polynomial to be 0. So what it means to split is the polynomial's degree n, and it has n roots, right? It splits down into a product of linear polynomials. Let me add to this definition by saying an extension field F star contained now is a splitting field for this polynomial. For F of X in F of X if F of X splits over F star or in F star of X, right? So it's linear here, and F star let me say splitting field over F, and F star is F adjoined with R1, R2. Okay, so what I mean by splitting field is it's a field that contains F. So I'll start off basically with some polynomial in F of X. A splitting field for that polynomial over F of X is a field where f of x splits into linear factors. And this condition means it's sort of minimal, right? So it's the smallest field that contains f that has, so notice that this has just enough things to make it split down because it's got all the roots, right? So for example, give an example or two to kind of, I hope, clarify this a little bit. F of x and qx, right? We'll let f of x be x squared. Now, does this polynomial split over q? No, because the roots you need are I minus I, neither of which are rational numbers, right? The splitting field for f of x over q is qi. Notice that this is the most economical field that contains q where this splits, because now this thing is x plus I, x minus I, right? Let me make a distinction here. F of x splits in cx. I think we'd all have to agree with that, but C is not the splitting field. Or f of x over q. Because C is much bigger than q adjoined with I, right? Much bigger. However, C of x is the splitting field of this polynomial over what field? There you go. That's right. If we consider if instead of considering this as a polynomial Q, we said, okay, I want my base field, I want my sort of starting point to be the real numbers, then C is the splitting field. That's because C is R. So as a polynomial in Rx, C is the splitting field. As a polynomial in Qx, C is much too big to be the splitting field. Everybody okay with that? Okay, so, all right, splitting fields, we've talked about them. And here's kind of a theorem for instance. Suppose K is the field and f of x is some polynomial K of x. We'll say that. Yeah. And suppose that my polynomial is at least degree 1, then there exists a splitting field. F of x over K. Say F. So there is a field where f of x splits that contains K, that's what I mean by over K, such that anybody want to take a guess at this? Imagine a worst case scenario. What's that? So imagine a worst case scenario. Suppose you've got an integer polynomial, right? Let's suppose that polynomials are this. So your polynomial is irreducible degree n, and you take one root and throw it into the base 50K. What's that extension's degree? If the polynomial is irreducible, that's a degree n. Agreed? Now, if you're lucky, you got some of the other roots automatic. But let's be pessimists, shall we? So suppose we throw that first root in, and so now what happens to this polynomial is when you lift it up to where you throw in one root, it's got a factor of x minus the root you threw in, and then now it's got an n minus 1 degree factor. What if none of the roots are there? Now that one's stuck and irreducible. So take another root and throw that in. What's the degree of the extension above that one? N minus 1, because you've lowered the degree by 1. Okay, let's imagine that everything stinks all the way up, right? What's your worst case scenario here? Right. Because so if you've got a 5th degree polynomial that's irreducible, you throw a root in. Well, now that polynomial factors into a degree 1 and a degree 4. If that degree 4 is irreducible, now you got to throw in another root from it. That'll factor into a degree 1 and a degree 3. You got no roots in that, so in a worst case scenario, for a 5th degree extension, you could be jumping up as high as a 120 degree extension to get all the roots, right? Okay, so I've sort of talked you through the proof, I think, but let's go through it anyway. And why is it a less than or equal to? Well, because at every jump you might get lucky, right? In the first one you throw a root in, it might. If you're really lucky, when you throw in the first root, you get all the rest of the roots, right? And in fact, we'll see a type of field where that actually happens from time to time. But that's where the less than or equal comes. The less than or equal comes from. You ain't get lucky. So what we're going to do here is proof. We're going to combine induction on n, which is the 3 x. If n equals 1, then right. So if it is 1, polynomial is linear, right? And the root is that sucker right there, which is already in K. So your splitting field is K adjoined with minus B over A. And now you feel like a total tool because it was already in there in the first place, which is K. So the degree of F over K is equal to 1, which is of course S centered. Okay. So there we go. Linear case, not a problem. Let's now suppose so with degree of F, so you suppose, well, here's our inductive step here. If degree of F of X is less than or equal to n minus 1, then there exists a splitting field for F for F of X containing K such that the degree of F of K is less than or equal to n minus 1 factor. Okay, so now suppose you have a polynomial degree n, and let G be any irreducible factor of F degree more than 1. So of f of x such that uh, actually, I'm going to do more than one. Now I'm sort of why am I selecting this more than one? So your first sort of sign of stress here ought to be, well, Jim, wait a minute. What if you don't have any? What happens? What happens if there aren't any irreducible factors of degree more than one? So what's that?
It splits, right?
That's right. We can assume this because you're all irreducible factors of f are of degree one, then f of x splits in kx. Because really, when you say that all irreducible factors are of degree one, that means that all the roots are already in there. Therefore, in this case, since little f splits in K, then the splitting field is F, because when you join all the roots, same as we did over here, when you join all the roots, they're already there. And one is less than or equal to factorial, so there we go. So we've got that figured. So now let's suppose we have so we will go back to our assumption here that there's at least one irreducible factor of degree bigger than one. So let U be a root. Get that. And note that U is not in K, because G is an irreducible factor of degree one. I'm sorry, of degree greater than one, so it's not in K. And the degree KU over K, remember what this is, right? If you remember that KU is actually equal to adjoining the root of G is the same thing as doing this. So this is equal to that is called, yeah. Which is bigger than one. Okay. So now over KU, well, in this extension field KU, I've actually got a root of G of X, right? Because U is the root of it. And so actually F, so U is of course a root of G, which makes it a root of F, right? Because G is an irreducible factor of F. So F of X has that factor of X minus U times H of X, where H of X is in and is of degree -1. Everybody okay with it? So here's where the inductive step kicks in. Notice that by induction, there is a splitting field for HVACs over KU of degree less than or equal to n minus 1. And I probably should call this something here. So here's our situation. Of course, in the field F, H of X splits down into linears because F is a splitting field of H over this. So in F, the original polynomial F of X splits as well, because all you need is a extra root U, which is certainly in F because F contains K of U. And this degree is right. And let's see what we can get here. This sucker right here that's less than or equal to n minus 1 factorial because that's our inductive hypothesis. And this is equal to degree of G of X. And I don't know much, but I know that that's bounded by n, right? Because remember what G of X is. G of X is an irreducible polynomial that, or I'm sorry, an irreducible factor of the polynomial f of x of degree bigger than 1. And so therefore, I don't know much, but I know that the degree of G of X, since it's a factor of f, must be of degree less than or equal to n. So this is actually less than or equal to n minus 1 factorial times n, which is n. And then there. Okay, any questions on that? Okay, before I forget, I apologize for this. There's a grad student recruiting we've got going on this committee. Anyway, I'm going to be out of my office from 10, it'll probably only be 10 to 10:30, I suspect, or 11 at worst. So if you're planning to see me then, just let me know and we'll work something out. But I'll be in my office 9 to 10, and then when we get back to the meeting, probably 10:30 to noon. Okay, give you another definition. So let's let K be a field. And F an extension. Okay, so you've got some field K, you got F, an extension field. My definition is we're going to say, we say F is normal over K. Or some people say F is a normal extension of K. If every non-constant polynomial in Kx that has a root in F splits in it. Or splits over it, I should say. So we say that an extension is normal. And of course, normal over something. This is I forgot an important word. Does anybody know what it is? Otherwise, there'd be almost no extensions for normal. They probably have to be alphabet closed. Let me see, make sure that I put the word in the definition. There we go. Yeah, by the way, this might be a good exercise. What important word? Well, I'm going to cover that with non-constant, but you're getting close. You're getting closer. So let me point out something. Suppose you have any polynomial. Now multiply by x minus 1. Right? This polynomial will have a root everywhere. And what if this is irreducible, right? I mean, so there'd be almost nothing that's normal if this would take place, right? I need to have every non-constant irreducible. Polynomial K of x actually splits. Because otherwise, all you'd have to do is take something that has no root and tack an x minus 1 on it. Now it's got a root, namely 1, and that, so there'd be almost nothing that's normal otherwise. Anybody know an example of one of these normal extensions? C. Oh, sure, that'll work. Yeah. Probably. Right. Actually, I like your example. Right, because notice again. This is why I had to correct my earlier thing. If you look at this polynomial, it's got a root here over R, right? But it doesn't split. But if you make that polynomial irreducible, notice this is by the way, C over R is a very interesting extension, right? Because notice that what do we know about complex roots that are not real, that are roots of a polynomial that have real coefficients? They have to occur in conjugate pairs, right? And so that's basically the argument that C is a normal extension, because you have to have conjugate pairs. So if you have one root that's not in R, then its conjugate is the other root, and its conjugate is also there as well. So it has to split all the way down. And also your observation that C is algebraically closed, that sort of guarantees that as well. By the way, this has an important calculus application. Every polynomial with real coefficients factors into a product of linears and irreducible quadratics, right? And that's a little bit, I mean, but even that one, right? By the way, anybody see that one certainly doesn't have any real roots, does it? Anybody see how to factor it? Right, factorization is the tricky part. I don't think that works. Yeah. Right, but that's not obvious. Right, but you can make an argument that, you know, if this has no linears, it's fourth grade, it has no linears, then basically there have to be two real quadratics multiplied and put together. So what's the calculus? If that weren't true, partial fractions would be a humongous waste of time, right? If you had real polynomials that were irreducible at every degree, I mean, you know, good luck with that, right? But because over the reals, your factorization into polynomials are either linears or irreducible quadratics, then you always end up integrating either something like this somehow, perhaps, or doing something like this. Or this is an irreducible quadratic. And both of these can be done. These are all with logs, and these are, well, it depends, right? But these are trig. You can do trig substitutions to get these, right? So that's kind of a nice application for that. Another good example, and this is a right down the path of this other one. If you look at, this is a normal extension. This is in fact a normal extension. Q inside QI, Q inside Q to the square root of 2. And basically the exercise is, you know, just basically use the quadratic formula. Let me get specific here. If you look at, let me break screen here. Well, actually, you know what I'm doing on the sheet because, or oh, that worked out pretty nice. Okay, so take this polynomial right here, right? This is irreducible over Q, right? Because if it were irreducible, if you could reduce it over Q, you'd have to have two linear factors, which means that both roots have to be rational, right? And conveniently, you can just check the rational root test here. And you can see that neither one nor negative one is proof, right? But okay. And in fact, the roots here are -2, square root of 4, and 4 is 8 over 2, -1 plus -1. Notice this number is in this field, right? Everybody agree with me? Because it's a rational number plus some rational multiple radical 2. Notice that because you've got the plus or minus radical 2, both roots are in there, right? So this is a normal extension. You have to get both of them. Of course, you can make the argument that quadratic extension, but so for example, if you look at this polynomial here, this one does not split in here, but that's okay because there's no root of this that's in here, right? And I'll give you one more example of an extension. I always like non-examples too. And so here's an old chestnut. This is not normal. Because if you look at this polynomial, It's an Eisenstein polynomial, so it's irreducible. It's irreducible over Q. This, it is not irreducible here, and the factorization is and it is x minus 2 to the 1/3, and whatever this is, right. Right. So I've got a root. So here's an irreducible polynomial. It's got a root here, but this polynomial doesn't split down any further, because to get roots of this, you need complex roots that are not real. They're not there. So that's a good example, but not normal extension. As you might guess, given the nature of my past couple of examples, there is an intimate connection between an extension being Galois and being normal. And we'll discuss that in a bit. In fact, they're very close to the following. So let me just mark. We will see that Galois, an extension is Galois, we talked about that before, is equivalent to normal and separable, which I have not defined what it means to be separable yet, but basically what it means is it means that if you, all the roots of the polynomial in question are distinct. So I'll make that a little bit more precise pretty soon. Actually, better. Theorem 8.4. Well, that would be a field. The following conditions are equivalent. And the fact that these conditions are equivalent, I think will be fairly straightforward. I'll probably talk through the proof a little bit, but might not write down all the details. Every non-constant polynomial f of x in f of x has a root, you know, B, every non-constant polynomial splits over F. C, f of x and f of x is irreducible if and only if degree of f is precisely 1. D, so this one kind of looks a little bit different, but later, there is no proper algebraic extension So you can't find any algebraic extension of F other than itself, in trivial case. And there's a field K contained in F, such that F is algebraic over K, and every polynomial, well, such that F is algebraic over K, and every polynomial in Kx splits net effects. Okay. I'll let you think about the last one here, but I'll talk through part of this anyway. A implies B. What A says is, I don't care what the polynomial is, it's got a root, right? So why does the polynomial have to split? Well, just take your favorite polynomial. It's a degree in, say. It's got a root. So now it factors into that x minus root comes a degree n minus one polynomial. But the degree n minus one polynomial has a root. So pull that root off. Now you got two linears times a degree n minus two, and just keep going, and it goes all the way down. If every polynomial has a root, it has to split all the way down in the linear factor. Okay, okay. How about the other implications here? Every non-constant polynomial splits. Okay, all right. Now suppose you have an irreducible polynomial, right? If its degree is bigger than one, it splits and is therefore not irreducible. And of course, if the degree is one and you're over a field, it's automatically irreducible. You don't even need anything for the other direction. This is the one that's kind of interesting. There is no proper algebraic extension of F, right? So let's do like, let's do D if and only if A. Let me write down the details of that. There is no proper algebraic extension of F, and well, actually, actually, I will use A through C. By the way, notice this condition means A, right? Is that pretty clear? C implies A, right? Because what you're saying is set of irreducible polynomials are precisely degree one polynomials. So if you've got a polynomial of degree bigger than one, well, if you got a polynomial of degree one, it's certainly got a root in F. If you've got a polynomial of higher degree, it has to factor down into linears, which means all its roots are in F. So let's do D if and only if A. So suppose well, actually, let's see here. Root positive. Suppose there exists f of x and fx with degree of f greater than 1, and f is irreducible. So this is a consequence of, so that is, suppose that you have a non-constant polynomial, or suppose this isn't true, then you have to have a non-constant polynomial that doesn't have a root in F. From this, you can extract an irreducible polynomial to degree 1. Agree? So well, let's let U be a root of F. X, and consider Oops, I guess I meant F U. F adjoined with U, which is isomorphic to Fx by Fx. And the degree of Fu over F is equal to the degree of F, which is bigger than 1, and is algebraic. So if there is a non-constant polynomial that doesn't have a root in F, you can just build this algebraic extension of the field, right? And that contradicts the statement B. On the other hand, let's do D implies A. Right, so there's no proper algebraic extension of F. Why does that mean that every non-constant has a root in F? Well, let F of X and suppose it doesn't have a root. So, right, and suppose F doesn't have a root. So we deny A, so there's a non-constant polynomial that doesn't have a root. Then let's see, what did I do last time? Did I get myself all playing around here? Yeah, I guess what I really did, I'm not paying much attention to it. I did didn't I do this here, right? So we started off and said there exists F of X that doesn't have a root, right? And so then we got we denied D. So that's what, yeah, we really did. Up here, we did not A implies not B. Yeah, so I'm confused over here. We did not A implies not B, which is A. Okay, so for the other direction, we want to do D implies A, right? Not A plus not B. So this D implies A. Yeah, that's right. So suppose every non-constant polynomial has a root, right? Implies D. Then we want to show that there's no proper algebraic extension. So if there is a proper algebraic extension, there we go. If there exists L containing F such that L is algebraic, then select U and L minus F. Right? This U is a root of some F of X in Fx by the assumption that right. So what we're doing is we're assuming that there is a proper algebraic extension. Since this is algebraic, there's a U here. This U has to be a root of some F. Right. Well, notice that F must split Yeah, that's. Right, because we showed that A, B, and C are all equivalent, so that's a shortcut. F of X was split, therefore. U is in F, which is. Because I tried to pick U in the algebraic extension, not in F. Okay. That's good for today. See if you can connect that up with E, and we will reconvene Wednesday. I'll be out of the office from 10 to 10:30 or 11 probably. If you're going to talk to me, come do analysis. Questions? Okay. Strap, any questions out there? If not, you all
I
have
think
a
I'm
good
fine.
day and see you on Wednesday.